Hey everyone. Okay, so here we go. This is my effort at making a sort of a Ben Eater style video. For those of you who don't know who Ben Eater is, he's a guy who's he has a YouTube channel and he's fairly well known for making videos like this of him putting together simple sort of computers, like really simple fundamental computers to help people understand how computer fundamentals work. And his videos are really good. I highly recommend them if you're interested in that kind of thing. But I wanted to make a couple of videos of my own just to show a sort of a project that I made. I actually made this project about 20 years ago and then kind of forgot about it after that. But I wanted to make a video of me putting it together on YouTube. The focus here is mostly on the hardware. There is obviously a software component as well to a computer, but I'm mostly not going to discuss that. I will just discuss how to put the hardware together because software is a big topic in and of itself, and I'm not really a software expert. I'm more of a electronics person than a software person, to be honest. So when you're doing stuff like this, your starting point is typically a breadboard like this. Unfortunately, it's very difficult to get a breadboard these days. If you're lucky enough to live in a major city, you might have a local electronics shop that sells these. Otherwise, you can usually get them online. There are places that sell them online. I mean, they're not extremely hard to find, but they are mostly a hobbyist item, and there are actually not that many electronics hobbyists in the world these days, so they can be kind of a rare item. But anyway, this breadboard is obviously pretty big. I recommend one that's got four rows. So like this is 1 row, 2 rows, 3 and 4. I would do it on one about this size. You can do it with less. I mean, I guess you could probably do it with 3 rows, but it would be a little bit more uncomfortable. I recommend one this size. Bigger is obviously also okay, but if you have one that's really huge, like even bigger than this, then it might be difficult to find room to put the breadboard itself, depending on how big of a table you have. Anyway, so yeah, so I was originally going to do this all as one huge video, but then I thought, nah, it's probably going to take too long. The video is going to be monstrously long, so I'll do this in a few parts. I think right now the plan is to do this in about 4 parts. So this is part 1, and obviously the star of the show, the main feature of the show, is the CPU itself, the 6502, which I have one of here, and I'm going to... By the way, I am grounded on my right arm. I am wearing a wrist ground strap, as you can see. You might not see it in the video because I'm mostly just going to you'll see my hands in the video, and you might not see the strap there, but it is there. Sorry, that black cord is the camera cord. I'll try to keep that out of the picture so as not to be too distracting. But yeah, the star of the show is, of course, the CPU itself. I don't know how well you can read that. It should be pretty readable. So you can see the logo of the WDC, the Western Design Center, which is a company that still specializes in making the 6502 CPU, as well as compatible chips like the, I think it's the 6522 interface adapter, which we'll see hopefully in a future video. But yeah, you can see this is the W65C02S. That is the model number of what I'm holding in my hand here. I believe W just stands for WDC, for the Western Design Center. It is Western Design Center, right? I think so, but hold on, let me see. Yes, WDC is Western Design Center. So I think the W just stands for Western Design Center. The 6502 is the original model of this chip. The C means that this is a CMOS version, and the S and the other stuff there, I actually don't know what that... I don't know what the rest of that means, to be honest. But it's a 6502. There are some differences between this chip and one that I used previously. I previously used, when I did this project about 20 years ago, I used a non-CMOS version of this chip from a different manufacturer. So there will be some slight differences that we'll need to be aware of from using, kind of a classic, let's say, classic... Couldn't see me doing the air quotes very well. Classic 6502, but I'll cover those as we get into it. And yeah, of course, I'm trying not to touch the pins on the chip, but I am sort of unavoidably going to touch them, brush them a little bit. But yeah, I have the wrist strap, so I should be okay, hopefully. I hope that my outlet here is actually grounded correctly. Okay, so... yeah, so the breadboard is not extremely hard to find. Where can you still get a 6502? Like I said, these are still actively made by the WDC, the Western Design Center, as of making this video. If you're in the US, you can probably still order one of these from the major US distributors like Janeco. I don't know if DigiKey has these, but Janeco should have them. They did have them in the past because Janeco is more oriented towards hobbyists. In Europe, I was able to order this from Mouser. Mouser has a local presence in many major European countries, so I was able to order this online from Mouser. You're probably not likely to find it in a local shop unless you get really lucky, but yeah, it's unlikely that you'll find this chip in a local electronics shop, so you'll probably have to order that online. So let's get started. So hold on, I printed out this, oh, it's a little huge actually, it's a little too big to fit in the camera, but this is the pinout of the 6502, so actually, you know what, let me fold it up a bit so that you can see. So yeah, so this chip has 40 pins. On the left side they're numbered from the upper left 1 to 20, and then on the other side they're numbered from 21 all the way up to 40 here. And yeah, we will want to pay attention to these pin designations because, again, they are slightly different from what you'd get in a classic 6502. But the first thing to do is to put the pin on the breadboard. So you orient yourself according to the little notch on the pin. So you can see there's a notch cut out into the side there. It's a little hard to see, but there is a notch cut into the center of the chip there. That means that's the side with pin 1. So this chip here in the upper left corner here, that's pin 1. So I'm going to go ahead and put this on the breadboard, and I guess I'll go ahead and put it, let's see, let's do it like this. So I'll put pin 1 on row 11 of the breadboard. That way we know that we need to add 10 to every pin number. So basically row 11 on the breadboard is pin 1 on the chip, and then row 21 is going to be row 10 on the chip. That should be correct, right? I believe that's wait, no, sorry, 21. Or, wait, hold on. Yeah, 20 is, okay, sorry. So row 20 is row 10, yeah, of course, because we're starting from 1. So 1 to 10, 11 to 20. So, sorry, okay, so row 20 is pin 10 on the chip, and, yeah, and then row 11 is pin 1 on the chip. That makes sense, right? I hope it makes sense. Yeah, because you can see it. So 30 is, so, right, okay, so 30 is pin 20, right? And then 20 is pin 10, and row 10 would be pin 0 if there were a pin 0, but there isn't. So 11 is pin 1 and so on. Okay, so you add, yeah, so you add 10 to the chip pin number to get the row number. The reason I'm doing it like that, I mean, I could put it up here so if there's a one-to-one correlation between the, we can't really see it that well with the camera angle, but I could put it at the top, but I want another chip up here at the top, so I'll shift this down by 10 like so. And getting the chip into the board is a little bit dicey. The problem with these chips is that the pins tend to bend outwards slightly. So on the left, you know, they're bent on this side, they're bent like that. And on the other side, they're bent like that. So, I mean, you can try to kind of push them in a bit, but it's a little haphazard because obviously you don't want to bend them too much. If you slip or if you don't have good control of the pins, you could end up bending them too much. I'm going to try to just push it in gently but firmly. And it's probably going to suddenly just click in with an alarming snap. Yeah, not damaging the chip at this point. I'm going to try and massage the pins in just a little bit, which is probably a stupid thing to do, but it seems to have worked. Okay, it's part way in, but I need to push it down a little more. There we go. Now it's really in there. Let me just quickly visually inspect it, make sure that it looks okay. Make sure that I didn't bend any pins. I think that looks okay. Yeah, looks good to me. So that's what it looks like on the breadboard. Okay, cool. So we've got that. So the chip is on the board. I guess that's the first step. Now we need the pinout. Let's go ahead and just go through the pins in order. So, pin 1, oh yeah, pin 1, VPB. Right off the start, this pin is important. On the original 6502, I believe this is supposed to be a ground connection. It's ground power. Let me just check that. Let me actually, give me a second. I'm going to go ahead and just check out the pin out of the original 6502 that I used. I know this is terribly exciting listening to me type off screen, but I just want to make sure that I get the right information because it can be confusing. Right, yeah, exactly. So originally, on the original 6502, pin 1 was VSS or ground. It actually had 2 VSS pins. There's one here, so in the corner here, pin 21 is still VSS, as you can see. But the original 6502, as far as I know, had VSS here as well. So it's a little bit disappointing that they've changed the pinout slightly because this is not necessarily a drop-in replacement. If you have a really old computer that actually used an original 6502, you can't necessarily just drop this in and say it's a literal drop-in replacement. You may have to modify the original hardware somewhat to be compatible with this version. It's a little bit unfortunate, but what can I say? It is what it is. So pin 1 is VPB, and I believe, if I'm not mistaken, that is an output. Let me just quickly check the data sheet for the 6502. Let's see, where is the pin list? Should be pretty close to the beginning. Here we go. Here are the pulls. Right. So it is the so-called vector pull output. So pin 1 is an output. In fact, let me actually let me just draw a little arrow on it indicating that it's an output. There we go. So you can see a line coming out of the chip indicating that's an output. So we won't use this. Originally, like I said, I connected it to ground. I connected pin 1 to ground because it's actually a ground power input. But you do not connect this pin to ground. That's a bad idea. I'll just leave it unconnected because I don't think we need that output for this project anyway. So you have to be a little bit careful. If you buy a 6502 from a different manufacturer or a different version, like maybe a non-CMOS version, be careful, be aware of what's going on because it may be that the pins are slightly different. Most of the pins are similar, but that one is not, and there's another one that's not. So pin 2 is ready. That just means that that is an input. That basically controls where the CPU is running, and that will need to be high. So let me just make sure. Yeah, so the point of that input is to actually control whether the CPU is running. You can actually stop it. So that pin is active high, meaning that when plus 5 volts is on that pin, then it's activated. Some of these inputs are active low. We'll get to those soon. But yeah, there you go. So pin 2 is now tied to the positive voltage, as you can hopefully see there. So that's pin 2. It's connected to the positive voltage. So the CPU will always be turned on, so to speak. If you want to halt the CPU, you can actually pause the CPU by sending that input to low, sending it to 0 volts. That will stop the CPU for as long as that's the case. But we won't need to stop it for this project, so we'll just tie that high and keep the ready signal on at all times. Okay, what's next? So pin 3 is phi 10. I believe that 0 means output, right? Yes. That is a clock output. Let me actually draw some arrows on this as we go along just to kind of be able to make some sense of this. So ready is an input. Pin 3 is an output. We don't need that for this project. That is, it's a clock output for external hardware, which we're not going to use. So pin 4 and 6. Well, what's pin 5? MLB. It's not Major League Baseball. I'm pretty sure about that. What is MLB? I think that's That's another innovation in this WDC version of the chip. So let me see, what is MLB? Memory lock. Memory lock is also an output, and we will not need that output for this project either. So, okay, so I'll just ignore that pin, and I'll draw resistors on 4 and 6. So now the diagram looks like this. So again, pin 5 is an output. That is something unique to this, to the WDC 6502. That's fine. We won't use that. We don't need that output either. But pins 4 and 6 for the two interrupt signals. So IRQ and the interrupt request, and the NMI, the non-maskable interrupt. These are active low. Is that right? They're active low, right? Pretty sure they are. Let me check. Where do we have... yeah. So, yeah, they're active low. So what I'm going to go ahead and do actually is tie them high. But I won't tie them directly to 5 volts. I'll run them to 5 volts through a 3000 ohm resistor. So this here is a 3000 ohm resistor. You can tell because the left band is orange. Well, that alone doesn't, that alone tells you the first digit is 3, but here on my table I have only 1000 ohm and 3000 ohm resistors. So if I see one with an orange band like that, I know it's got to be 3000 because I don't have anything else here right now. So let's go ahead and do this then. So we'll tie pins, what was it, 4 and 6, I believe? Yeah, 4 and 6 we'll tie to positive 5 volts. We could probably tie these directly to the positive side of things because we're not using them. Like, we're not using interrupts for this project at all. But the official documentation says you're supposed to use 3K pull-up resistors for these. I mean, I guess the point of that is so that they get pulled up if you use an interrupt. Since we're not using an interrupt, we could theoretically just forget that entirely and just tie them to high. But the documentation says to use 3000 ohm resistors, so just so that we don't do something silly, I'll go ahead and leave it like that. So now we have 2 resistors, tying those to high voltage to make sure the CPU doesn't get any interrupts. I drew these little zigzags to indicate resistors. You can tell I'm an American because I draw resistors that way. Europeans just use a rectangle for a resistor. Okay, moving on. So far so good. Pin number 7 is sync. What is that? Is that an input or an output? I believe that's an output, but let me check. Yeah. Sync is an output. We will not need that either. So I'll go ahead and draw an arrow on it. So now you can see 7 is an output, not used for this project. Okay, and then pin 8 is VDD, which means power in. That should be plus 5 volts, right? Yeah, VDD is the positive power supply. So I'll just write here plus 5V, plus 5 volts for pin 8. So that's fine. So let's go ahead and tie pin 8 to the positive side of our power supply. Let's see, that's this pin right here. There we go. Oh, I think I put it in the wrong place. I put that in the wrong place. Sorry, that's actually, yeah, sorry, that's pin 9. Duh. It's hard to see. So here we go. Let's try this again, this time with less failure. There we go. That looks good to me. So that's what we've got so far. Pretty simple, but hopefully auspicious beginnings. Okay, what's next? So Now we have the address bus, and I'm actually just going to leave that unwired for now. So we're going to do a really super simple test circuit right now, which means leaving the address bus unconnected. So I'm actually just going to ignore the address bus completely for this first video, or I'm going to use it later for testing, so I will test later using the address bus pins, but for now we'll just leave them unconnected. They're outputs, they're all outputs from the CPU, so we can use them for checking what the CPU is doing, but I won't connect them to anything right now. Okay, so what we have here is VSS, which is ground. I'll draw a ground symbol on it. There you go. Now you can see there's a nice little ground symbol showing that that is in fact ground. So let me go ahead and get a wire to put on the ground pin. And that will need to be a bit longer because ground is on the other side, on this side. So negative voltage, or 0 voltage actually, goes to ground. Very nice. So here again we have more address bus and the data bus. I'll come back to the data bus in a bit. First let's finish off the rest of these pins here. RWB that's the read-write output, right? Yes, that is also an output. That becomes very important later, but for this extremely simple project we're not even going to use that. So that's fine. That's an output, but we won't use it in this video. NC means not connected, so don't connect that to anything. BE, now this one really messed me up at first. This one confused the heck out of me when I first started using this version of the chip. Pin 36 on the original 6502 is, I believe, not connected. Let me check that to be sure. What is pin 36? Yeah, on the original 6502 it's not connected, but here it is BE. What does BE mean? Well, if you look in the manual, it explains BE is bus enable. That is an input, and it basically, as the name suggests, it enables the address and the data buses. You will not get any output on the buses if there's no input to bus enable. The buses are disabled, so you need to actually turn that on. You very definitely need to turn that on. So that's going to draw an arrow on it to indicate that that's an input. So you can see here BE is an input. Yeah, so if you're using this version of the 6502, don't forget to turn on BE if you want to use the buses, which you probably will want to do because otherwise the CPU is kind of useless without its buses, without the address and data buses. So I will want to, and BE is active high, so we will want to tie it to positive 5 volts. So it's the 5th pin from the top on this side, so 1, 2, 3, 4, 5 should be that one there, right? I believe that is accurate. Let me just quickly check. 1, 2, 3, 4, 5. 1, 2, 3, 4. Yep, 5th pin from the corner on that side. Okay, good. Okay, next pin. Phi 2. Phi referring to the Greek phi symbol, which is often used as a symbol for phase, because this is the clock input. This one is the clock input, right? Let me make sure. That should be the input, I believe. Let me check. Yeah. So that's the clock input. That becomes really important. That's extremely important. I will get back to that in a second. SOB is not what it usually stands for. It's set overflow, and I believe that's just to set the overflow flag on the CPU. We don't really need that. We don't really care about it, but I believe it's an input. Let me just make sure. Set overflow is an input, right? Yeah. So what I will do... What did I originally do with set overflow? I think let me check. check. Sorry, I'm just looking for it because I wrote some notes on this a long time ago. On my website, I actually still have the site where I mentioned how I did all this, but I'm just looking through it now, trying to find it and realizing it's not very... Yeah, okay. So the SO pin, so the set overflow pin is active low, so we'll just go ahead and tie it high. We'll just tie it to the high side of the power supply so that it doesn't connect to anything. I think the very first time I did this project, I left set overflow unconnected, and it worked. I mean, like it should still work, but yeah, you don't really want to leave pins unconnected, like inputs, especially you don't want to leave inputs unconnected on a CPU because it can lead to weird floating states inside the CPU. So yeah. So let me go ahead and just draw on this and indicate that set overflow is an input, and we've got that. We've got it covered. Okay. Phi 2 O, so the O means output. This is an output. We will not be using that, right? Yeah, that's an output, so we can just forget about that. So that's an output. And then the last pin there is reset. That resets the CPU. You will need to make a good reset signal, and reset is active low. That's correct, isn't it? Yeah, reset is active low. So what we will need to do for this is, let's see. Let me get another 3 ohm resistor. Here's one. And I'm going to go ahead and attach the reset pin to the positive power supply. I'll do that up here. It's a little up there, but that's okay. That should be okay. So there we go. Yeah. So it looks like this now. So what that resistor does, what that pull-up resistor does is when we're not doing anything else with the reset pin, it goes high so that the CPU is not constantly being reset. But when we connect it to low, we want the CPU to reset. So we need a button. And I got a nice little push button like this. It has 4 little legs on it, and I think this side is not connected with this side until you push the button. So when you push the button, all 4 pins are connected, but when you don't push the button, I think these 2 are connected to each other, but they're not connected to those 2. So what I'm going to go ahead and do, I'm not good for space here. The problem is I don't really have a good space to put the button here because I'm going to put another chip up here as well. So you know what I'll do? I'll do something a little bit ugly, and I'll take a long wire, and I'll put this long wire on the space for the reset pin if the wire wants to go in. This breadboard's decent quality, but sometimes it's really hard. It's really stiff, actually. It's really hard to get the wires in. Okay, so I'll run the reset signal way down here, let's say. So it's normally high, but we'll do something here to make it go low when we push the button. So what I'll do actually is, I guess I can just put the button here. I mean, that should work, theoretically. Yeah. And then I'll tie this side of the button to ground. So I need a wire like this one. There we go. Okay, so what I've done is the button is, so the left side, from this perspective, the left side of the button is connected to ground. When I push the button, it also goes through the wire and connects the wire here to ground. So that pin of the CPU, the pin here in this corner of the CPU, will be connected to ground when I push the button. When I don't push the button, it gets pulled up to high using that resistor. So that's a simple reset circuit. It's a little bit dirty because, you know, these kinds of push buttons, when they're operated by a human finger, there is some noise associated with them. Like when you release the button, it doesn't just magically spring high. It doesn't just go from 0 to 1. It kind of, there's some jitter. It kind of, it shakes. Like the signal shakes for a fraction of a second, and it's not really clean. It's always worked when I've tried it, so I'm not going to do anything differently this time. If you want, there are dedicated reset chips that will do a timed reset that, it's a little bit cleaner. If you want to make a really properly functioning computer, you can use something like that. But this is just, this is just a test that I'm just doing. I'm only going to run this for a few seconds. When all this is done, this is only going to run for a few seconds. It's hours and hours of work for a few seconds of activity. Or we've actually literally like a fraction of a second of activity, actually. So it's not something that needs to run for a really long time. So I'm okay with just using the button. If you want to do something nicer, go ahead, feel free, but this should be okay for now. So, okay, so that takes care of our reset signal. We're not using that. That is connected. So what's left? The clock input. B is connected, that doesn't matter, that's an output, and the data bus. So I think we just need to worry now about the data bus and the clock input. Is that right? I think that is right. Let me just take a look at the board and make sure. I'm just doing a quick once over of the board and make sure that I didn't forget anything. So yeah, that looks good. That looks good. That should be okay. That's okay, I think. Yeah, got that. Yeah. Good. Okay. Okay, so we've got everything taken care of now except the clock input and the data bus. I'll go ahead and do the clock input first. So for the clock input, I'm using an old circuit that I found on the internet. That looks like this. So this is the circuit that I used in the past. It works well enough. It's not, it's a pretty standard circuit for stuff like this. So basically, you use a quartz crystal, which I have one of here. You can see it says a 2 megahertz crystal. I have here indeed a 2 megahertz crystal. You can see it says 2.00 minus 20. That means 2 megahertz, 20 picofarads. And China must be some strange code word. I don't know what that is, but so that's the actual crystal. And here we have a 7404 chip, which is actually just a simple inverter chip. And I happen to have one of those right here. So let me actually go ahead and put that on the board now. That's the other chip that I said I was going to put on top of the CPU. Is that this one? Yes. Yeah, that should be this chip here. I'm going to show it briefly. You can see it's not just any 7404, it's I don't think the camera's focusing on it that well, but it's a 74F04. And I believe the F stands for fast, so that means that it's a little bit faster than just your typical sort of 74LS04, which is kind of important because we are using this as a clock generator or as part of a clock generator. So it needs to be pretty fast because this is going to run at a speed of 1 megahertz. It's going to give a pulse to the CPU 1 million times every second. So it needs to be pretty fast. Once again, there's a notch on the top of the chip to orient yourself with. So, okay, let's see. What do we have here? So I'll go ahead and connect the power first. So here we have 5 volts in and then 0 volts out. That's the power for the chip. Let's go ahead and do that now. So let me get an orange wire. And I will put that on this here. There we go. And the other side, I don't really have good. Okay, I'll put it up a bit. That should be okay. That should be okay. Do I want a yellow wire for this? Is that going to be long enough? Is that about the right length? It's a little bit awkward because there's a gap here in the power bus at the top. Is that long enough? I think that should be okay. Looks all right. Yeah. Yeah, there we go. Good. Okay, cool. Okay, so it looks like that so far. So plus 5 volts here and 0 volts there. Good start. Okay, So what's the rest? What's all this nonsense now? Basically, what the crystal does, the crystal acts as a bandpass filter. So, you know, if you studied in electronics class, there are low pass and high pass filters. I'm going to draw a quick diagram to show what they look like. Right, so they look kind of like this. So basically what you have, so I've drawn two small graphs here. The bottom axis is the frequency, and then this is just the vertical axis is the amplitude, the strength of the signal. So low pass filter, what it does is lower frequencies go through, but as the frequency goes up, it starts to get cut off. So it blocks higher frequencies. A high pass filter does the opposite. It blocks low frequencies, but as the frequency goes up, it starts to get stronger. It starts to get not amplified, but, you know, let through. And so that's what a high pass filter does. But then there's a so-called band pass filter, which looks kind of like this. So there's a specific frequency in the middle there that it wants to pass. Now, this is basically, if you remember old radio receivers, you know, where you'd turn the knob to tune into a frequency, this is basically what a bandpass filter does. It allows through that one frequency and blocks everything around it. So if you got a radio receiver and you want to receive a radio station on, I don't know, let's say 100 megahertz, you tune it to 100 megahertz so that this would be around 100 megahertz, and that would then block out all other frequencies, and you would just get the signal on that band. I've drawn it like this because a typical bandpass filter, it has some slop on it, like it's not perfect. That's one of the reasons why, you know, if you had an old radio receiver, or if you have one, you might have noticed that you can be tuned to one station, but there will be a little bit of interference sometimes from another station with a close frequency. Like you'll get this station really strongly in the middle, but if there's a station like with a frequency that's close to it, it'll kind of like, you'll sort of hear it quietly, like it'll play not as strongly, but you'll definitely hear it. You know, it's something that happens. So a typical bandpass filter like this is not perfect. An ideal bandpass filter, like a really ideal one, should just be a line. It should just be a vertical line like that. It just lets through that one frequency and nothing else, nothing around it. But most filters are not that ideal. They're not that perfect. But the crystal, these quartz crystals, they act as fairly ideal bandpass filters. So they do a pretty good job of just passing that one frequency, in this case 2 megahertz, and blocking everything else. So what we've got here, the reason why we're using this chip is because it has internally, it has these gates, which, yes, they are inverters, but we're not really using them as inverters. We're just using them as analog buffers to make sure that we have a nice, sharp, either 1 or 0 signal. We don't want this signal, you know, kind of wallowing around or sitting somewhere between 1 and 0. It needs to be a good clean cut from 0 to 5 volts and back down to 0 volts. So that's basically the only reason we're using this chip. It just gives you a nice clean cut because these inverters inside, again, we're just using them as analog kind of, you know, comparators, if you will. And then this whole thing with the resistors here and the capacitor there, this is just a feedback element because you need to get some feedback. So basically all we have here is we have just a big amplifier. So this consists of an amplifier with the crystal acting as a feedback element in the amplifier to block out other frequencies. And then this is also a feedback element so that you get some noise, kind of get some noise going so the amplifier can feed back into itself, because it will need to feed back into itself. You can see here it calls for a 0.05 microfarad capacitor. That does not need to be exact. The capacitors that I'm using here are, I think, so that's 50 nanofarads. 50 nanofarads, 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 50 nanofara I forget how to read capacitor numbers, but I believe this is, if I'm not mistaken, this is a 22 nanofarad capacitor, which is less than half of the prescribed value here, but that should be okay. It doesn't need to be exactly 50 nanofarads. 22, I mean, it worked for me when I tried it, so it should be okay. So that's really it. So the circuit's not really that special. If you're not really clear on how it works, you don't have to be. It's kind of a little bit magic. There's a little bit of magic at work here. I mean, it's obviously it's not magic, obviously it works, but this is more analog stuff. You don't really necessarily understand exactly how this works. Just build it and just trust that it'll work. You can also get besides 2-pin crystals like this one that I have here, you can also get 4-pin crystal modules, which are kind of this whole thing self-contained. So basically those things have 4 pins, but one of them is not connected. So you only have 3 pins that actually do anything. So the 3 pins that do something are just power in, power out, so like 0 volts and plus 5 volts, and then the 3rd pin is just your clock output. But we're doing a little bit more complicated here, just just for fun, just because doing this kind of stuff is fun, right? So let's see. So what I'm going to do first, actually, because this is a very small element here, I'm going to put a direct jumper between pins pins 4 and 5, right? So pins 4 and 5 will be shorted to each other on this. That output will be directly connected to this input. So pins 4 and 5, I'm going to use a teeny tiny jumper wire like this. And let me actually pick up the board for a second because I want to be sure that I stick this in the right place. It's going to be hard to get out. It's going to be hard to get out later if it's in the wrong place. Come on, get in. There we go. Right, so that was pins 4 and 5, right? Yep, looks good. Okay, so far so good. So now it looks like that. You can see the jumper wire there. Okay. What's next? I guess I'll go ahead and put the capacitor in. That goes between pins 2 and 3. So that should go right about there. That looks okay to me. Okay. And the crystal, I guess we can put, so the crystal goes between pins 1 and 4. So that should go like that. That should be okay. I apologize, the lighting is not very good here. It's hard for me to see as well. But yeah, so it looks like that so far. So now we just need to put in the 2 resistors. And this is a bit tricky. If you really want to do this nicely, you should probably trim the leads on the resistors down because these resistors are stupidly long, but I don't want to. I probably should. It's not like I'm short on resistors. I have a pack of these resistors, so I should probably trim the leads on them to make them easier to deal with. But yeah, I'm just too chicken to do that because I'm always worried that I might need the longer leads later, and I really won't. I mean, if I'm just going to use them for this, I really won't need the long leads. Problem is these resistors are very susceptible to bending because the leads are so thin. Whenever I try to put them into this breadboard, the leads are more apt to just bend in place rather than actually go into the holes. That one actually went in pretty well, though. That was all right. That was pretty okay. Let's see if I can get lucky like that a second time. Where's my other resistor? Here it is. And yeah, these resistors are very small. They're kind of hard to see, but I know they're 1K resistors because, yeah, the first band is brown. So we are going to put this guy there like that. And yeah, the problem also is you don't want these things to touch each other. You don't want the resistors to touch each other because that could mess with the signal. I think that's okay. I think if I don't mess with it too much, I think this configuration should be okay. Okay, that looks all right to me. So I'm going to go ahead and leave that like that. So everything's in place now except the actual clock output. So you can see pin 6 here is the actual clock output to the CPU pin. So let's go ahead and take a nice wire and put this on pin 6 of the of that inverter chip, and I will run this over to the clock pin on the CPU, which was, what pin was it? 39. Wait, no. Duh, no, that's an output. 37. Derp, yes. Pin 37, so the fourth pin from the corner there. So you go right there. Nice. And that should be it. That should be our clock circuit for the CPU. That's what generates the actual square wave, which basically tells the CPU how fast to run. It basically triggers each pulse of that clock will trigger another cycle of the CPU. If I had an oscilloscope here, I would turn this on and check it. I would check that clock output right now to make sure that it looks good, that it's actually giving a good, clean square wave signal at an appropriate speed, which should be about 1 megahertz, or even 2 megahertz would be okay. I actually don't know, because this is a 2 megahertz crystal that we're using here, I actually don't know if that means it's a 2 megahertz signal or if it gets cut in half. I actually never bothered to research that. It doesn't matter too much. The CPU should be capable of running at 2 megahertz as well. It's kind of overclocking it, but I think that should work, maybe. At least it worked when I tried it. Yeah, but unfortunately I don't have an oscilloscope here, and the apartment that I'm in didn't come with one. It's kind of weird. Like, you know, when you rent an apartment, you always get useless stuff like there is typically a fridge and a stove and an oven and things like that. I mean, who uses stuff like that? I mean, they could have left that stuff out and used that space to put in an oscilloscope and a soldering station, you know, things like that people would actually use. But no, I don't have anything like that here, and I didn't want to go out and buy an oscilloscope just for this one project. We'll just hope that it works. It should work. I used these components all before. They did work, so they should work again this time. So that's it now, except for the data bus. So what we need to do is, since we're not using actual memory for this very simple first start, what I want to do is actually manually wire the 8 data bus pins to generate an NOP instruction. NOP stands for no operation, and basically, let me look up the code for NOP. What is the CPU opcode for NOP? It is 1110, so I'll go ahead and write this down, 1110, and then 1010, so 1010. So basically all that the CPU is, it's just a big instruction runner. All it does is it to instructions that you give it. And the instructions all come in on these 8 pins. It's an 8-bit wide data bus, and the instructions are then 8 bits wide. So, like I said, there's actually an instruction called NOP, which means no operation, and the code for it on the 6502 is 11101010. So if that number, like if that set of inputs comes in on the data bus when the CPU is looking for an instruction, it will execute a no operation, which simply means it jumps to the next byte in memory and looks for the next instruction there. We don't have a memory chip. Well, I mean, I have a memory chip, but I'm not going to use it for this first video. So what I'm going to do actually is tie all these data bus pins directly so that they go directly to either 1 or 0. I could just use wires for that, but just in case the CPU tries to write to the data bus pins, it would be bad if the CPU tried to output something and it output directly to, to the positive or negative rail of the power supply. So rather than doing that, I'm going to go ahead and run these signals through more 1 ohm resistors. So let's go ahead and get started with that. So these pins might be counterintuitively numbered. So data bus pin 0 is actually on the right side, and data bus pin 7 is on the left side. That means this is D0, D1, D2, D3, D4, D5, D6, and D7. So that means that D0 needs to go to 0. It needs to go to ground. And I've just dropped a resistor on the floor. Where did it go? Where did you go? I might have to find it later. I don't feel like it could have gone that far, but I do not see it now. Okay, that's fine. That's okay. I'll look for it later. I have others that I can use. So, okay, so this is then 1, 2, 3, 4, 5, 6, 7, 8. So this is pin 8 from the corner. So 1, 2, 3, 4, 5, 6, 7, 8. So I'll go ahead and put this here. And to give ourselves a bit more room, I'll run this resistor upwards, like so. So, yeah. Okay, so D0 is 0. This is obviously pretty time consuming. In future videos when I do stuff like this, I'm probably going to pause the video, but just for this one round, I think this is only 8 resistors. It's not that onerous, so I think we can survive with leaving the video running for this one just to kind of get an idea what's going on here. So D1 is 1, so I'll go ahead and run this to positive 5 volts. There we go. These resistors are a little resistant to go in. Lol. Okay, D2 is 0. So I need another resistor here for D2. And, right, you go to ground because that will be 0. Come on, get in there. Wow, the combination of the resistor wires being very thin and the breadboard inputs being very, very stiff. Okay, so that was D2. Now we want D3. And D3 is a 1, so we'll run this to positive 5 volts. I guess we can just put that here, for example. Okay, that looks fine. Next one is D4, and D4 is a 0. So I'll go ahead and run that down there. And obviously, it's important that these wires don't touch each other. It's important that they don't short. So this is really precarious to do with uninsulated resistor wires like this. I mean, visually I can see if they're touching, but it's, for big projects, like if we're going to do like a really big thing with this, I wouldn't recommend doing it like this. It's not really good. It's not a great way to do it, but we're still starting small, so we should be okay. So I have 5 already here so far. So the remaining 3 are all 1. So all the remaining 3 go to plus 5 volts. There's 1. And here's running out of room to put these nicely. Another one. And the last one. So that is 1, 2, 3, 4, 5, 6 from the corner there. Yeah, that looks right. So this is also a binary 1, so it should go to plus positive voltage. All right, I'm going to do another quick visual check just to make sure these resistor wires are not touching each other, that they're not shorted. They look okay to me. Okay, good. So that's it. We're done. We've done with the wiring. So what should happen now is when we turn the CPU on, it's going to constantly get a no operation signal on the data bus, and it's just going to continually operate no instruction over and over. So let's go ahead and give this a try. I'm going to go ahead and turn the thing on. Good. So I've connected power now. You can also put a power, if you want, you can put like a power LED on the board so you can see when power's on, but the power should be on as far as I know. And I'm going to go ahead and press the button. The CPU will need to be reset once before it starts running, so just push the button, release the button, that's it. That should reset the CPU, and the CPU should now be running. Now the question is, how can we check on that? Well, you might have seen this little LED off to the side, so I'm going to use this LED for testing, which is also not really a great thing to do, but it's what I'm doing because that's what I have. So I'm going to go ahead and stick this LED here on, let's see, do I want to do that? Maybe put it like, I was trying to think where's a good place to put it where it's not going to, put it down here. Yeah, the camera should be able to see that. Yeah, that's actually, it's in good view of the camera. So okay, so the one side of the LED is directly connected to a negative here, and this will be the positive side. What I'm going to go ahead and do then is get another resistor. Where do I have another? I'm going to want another 1 kilo ohm resistor to use with the LED. I could use the one that I dropped if I could find it. I can't believe it just disappeared. How does stuff just disappear when it falls down? It's really, okay, whatever. I'll look for it later. I'll just pull a new resistor off my reel. Then I've got a reel of resistors, so it should be okay. I don't think I'll run out for this project. Okay, so I will run this resistor thus. And then I'll take a long wire and connect one end of the wire like so. So basically, whatever I touch this loose end of the wire to now, if I touch this to a positive voltage, it should turn the LED on. Let me test it with the positive rail of the power supply. There we go. It turns on. So if I touch positive voltage, it goes on. And obviously if I touch a negative voltage, it does not go on. So let's try probing some of the CPU address bus pins. I'm going to leave that wire there just for a second. So the CPU's address bus starts here. It goes all up this side of the CPU and then comes up this side of the CPU. So pin 25 is the highest bit of the address bus. So if we probe some of these lower lines, we probably won't see, let's see what happens. I'm guessing that we won't see any pulsing. But yeah, the LED is on. Now, if I'm not mistaken, it's not actually solid on, it's actually pulsing on and off, but it's pulsing so fast that the eye can't see it. So what we probably want to do, let me put this on the highest pin, so pin 25, A15, the highest pin of the address bus, which is actually right below the last data bus pin. There we go. Now, I don't know. Wow, it's actually kind of hard to see it pulsing even there. But I can just very faintly, like visually, I can just very faintly see that it is flickering. So basically what's happening here is the address bus is 16 bits wide, which means it can have a maximum of 65,000 and some values on it. So what's actually happening here is the CPU is starting from 0, it's counting from the bottom of the address space, and then it's counting all the way up to byte number 65,000 and some in its address space, and then when it's done, it goes back. So this pin here should pulse, like this should turn on whenever it gets to the top of the address space, and then it goes off when it finishes and recycles back to byte 0 of memory. The CPU should be running at 1 megahertz, which means that it's actually, how many times does 65,000 go into 1 million? Because it's doing 1 million cycles a second, and it's doing this, it should be pulsing this pin every time it hits 65,000. So I believe 1 million divided by 65,000 is something like 15. So that should be flashing at 15 hertz, which is just about slow enough that I can perceive a little bit of flickering. Again, I don't know how it looks on the camera, but I can see that it is flickering. So the CPU is actually counting. If I had a proper logic analyzer here with like 16 logic inputs, we could put the probes on the 16 address bus pins and actually see each address bus pin counting up. But I don't have anything fancy like that, so I'm just troubleshooting with an LED here, and you can see, I can see the LED is flickering. Whereas if I put this wire on the next address bus pin, yeah, I don't perceive any flickering now. It just looks on solid to me. And the other pins will be the same. They will all be flickering, but they'll look on solid because they'll be going too fast for you to perceive any flickering. So that's good. That means that we have a functioning CPU. The clock signal is working because it is actually clocking the CPU. The CPU is running. It's running based on that clock signal. And it is actually following the NOP, the no operation instructions that it's getting. So this was a great success. Great success. Very nice. So we have a running CPU. That's the first step. And not necessarily the biggest steps. Other future steps may be more difficult and involve more awkward wiring here, because it is kind of awkward sometimes to do this on a breadboard like this. But that's the first step. We've got our CPU, and yeah, that's actually it, really. If you want this to run really stably, a nice thing to do is to get a capacitor like this. This capacitor is, what's the rating on it? 0.15 microfarads, so basically 115 nanofarads, which is a good value to use to stabilize the power. If you want, you can put a capacitor like this between the positive and negative power pins on the CPU. That will stabilize out any power blips. So if the power wiggles for a second, or if it glitches for a second, this will basically absorb any transients that are on that on that line, so to speak. Again, if you really want to make it nice, make it reliable, and make it more solid, like less crash prone, you can use something like this and just put this on the 2 power pins. But I'll leave it off for now because this does not need to work consistently. It really just needs to work for like the few seconds that we're looking at it. So, and if the CPU does crash for whatever reason, we can just reset it. We have a reset button here. So I press the reset button. The light goes on steady, and then when I release the reset button, the CPU starts running again, and the LED starts flickering. Again, I don't know if you can see, you should, oh, I see. Actually, I guess it just freezes on wherever it was. So if it was off, then it stops there, and if it was on, then it stops there. So it might stop at on, or it might stop at off. Okay, whatever. It just freezes the CPU. So the CPU is now resetting, and when I release the button, it starts running again. So there you go. So everything should be working. That's it. That was the 6502 CPU that was getting it running with a very simple test circuit using constant NOP instructions as done by resistors on the data bus. Next time we'll actually introduce some memory to this, and we can actually start having some proper instructions fed into the CPU, have it actually do some instructions that it can be programmed with. So that'll be next time. Until then, thanks for watching, everyone. Hope it was interesting, and I will talk to all you folks later. Ta-ta.